There we go. Yeah, so what we have done in the last class, we did the energy stored in the capacitor, right? We got those equations down. The energy stored or the work done in charging the capacitors is half QV is also half Q squared over C is also half CV squared. This is a very commonly used equation. Half CV squared. So this is the energy stored in a capacitor, and I derived it by both ways, right? The integral approach and also the summing of the areas. So basically area under the triangle of a graph of Q versus V gives you work done, okay? And we also discussed how the capacitance of a capacitor is affected by the introduction of a dielectric. Yeah? And I gave you two situations where the introduction is going to affect something. How a capacitor's capacitance increases due to the introduction of a dielectric online and offline. You understand both? Online means when it is plugged into the power supply. Then what happens when it is plugged into the power supply? You put in the dielectric. As soon as you put the dielectric, there is a negative voltage set up inside the dielectric. That reduces the overall voltage, and therefore the battery voltage will be higher than the overall voltage there. So what will happen is there will be some more charges being pushed into the capacitor. So the charges will be pushed into the capacitor until the overall voltage matches with what is applied. So since charge is actually increasing, the new capacitance is going to be affected by the new charge. The potential difference across the capacitor is the same as what is being applied. So if you apply 12 volts to the capacitor is still going to get 12 volts, but the charge will increase. How many times does this charge increase? The same number of times as the permittivity, the K increases, dielectric. So capacitance increases by K. Capacitance increases by K, charge increases by K. That's the situation online. Now offline situation is actually you charge the capacitor and then disconnect the battery. So now we have a charged capacitor and there's no battery connected to it. It's charged to Q coulombs and to V volts. Now what happens when you introduce the dielectric between the plates? As soon as you introduce the dielectric gets polarized because of the field, and that will create a negative voltage which will reduce the overall potential difference. So the potential difference is going to be affected in that case. The charge cannot be affected because charges cannot be created nor destroyed. Since there is no source of extra charges, we have disconnected the battery already. Charge stays the same, but the voltage drops to a new voltage, which is basically whatever you applied minus whatever you applied earlier minus the potential difference across the dielectric. And that, so how many times is the voltage going to reduce? The same K number of times, K or epsilon R. And because it is reducing that many times, the capacitance increases the same number of times. So capacitance is a property of a capacitor which does not depend on the voltage or anything like that. It depends on its own characteristics. And so we saw the equation for capacitance is equal to epsilon naught area over the distance between the plates. Correct? And if the K comes in, then introduce the K here, right here. So then the capacitance with the K is going to be epsilon naught K A over D. K also means epsilon R. So we have gone through the capacitance equations, and okay. Now what happens when a capacitor is charged? Let us go deep into it. When a capacitor is connected to a power supply, when a capacitor is connected to the power supply, the power supply is V volts. As soon as you connect the capacitor across the power supply, charges are going to flow to fill up this, right? The charges are going to flow so that it will create charges on the plates of the capacitor. So will there be a current right here? Will there be an electric current in the circuit while charges are being dropped there? Yes. Is this current a constant current? No. When is the current maximum? In the initial moments. So because there was no potential difference here to start with, this is full of potential difference. So the potential difference here is V and there's nothing. So the overall potential difference is V volts and there is hardly any resistance here. So therefore the current initially will be the highest current. And that is what starts, that's what charges this up. But as soon as small amounts of charges drop on the plates, then it establishes a small potential difference. So this is 12 and that is 2 perhaps, and therefore the net potential difference is now not 12 anymore, it is lower. And because it's lower, this current will drop. So the charging current will start dropping. And finally, when this is 11.99 and this is 12, there is a little more charge, that can still go through there. So a little more charge will trickle down there, and then finally once this is 12 and this is 12, it just stops the whole thing. Now, what I'm talking about is just fractions of a second. So you saw me when I connected the capacitor directly. There was hardly any resistance involved. So as soon as I connected, just touched it, the capacitor is already charged. It's already charged. I was just holding on to it so that it let it reach the max. But the moment you kind of touch it, I touched it to about 200. And the moment I touch it, it is almost nearly 200. But I just wanted to fill it up so that it is like, so you could hear the sound of that operation also. As soon as I touched it, there was a sound that was actually growing. And then finally the sound finished. The sound effects is all basically because of the, those are parallel plates. So as soon as charges start going onto the parallel plates, it is kind of creating a sort of vibration. And the vibration is not on the capacitor, it's actually from the transformer. Because when current is delivered, the transformer is doing work. This is a magnetic kind of vibration. Alright, so the current initially is the highest and then finally the current goes down to 0. So if you put a light bulb here, what we'll see on the light bulb is the light bulb will come on for full brightness initially and then fade off to 0. And this will take place in very little time. So if you don't have anything else, now the bulb has its resistance, right? The bulb has a resistance. Therefore, you won't get a very high current to start with. It will be a fairly good amount of current, which will cause the light bulb to glow. And then it will just go down in intensity, right? Now, if I put more resistance here, then it will slow down that same process, but eventually it will probably light up for more time. If I put resistance, it delays the whole process. How can you check if the capacitor is bad or not? If it is a shorted capacitor, like the ones which I showed, if it's a shorted capacitor, the light bulb will stay lit because that's shorted. The light bulb will stay lit. Do you get it? Well, you have to put the light bulb of something that can accommodate that potential difference. If you take a light bulb of 2 volts and put it on 12 volts, that will blow up. So you have to put the light bulb of 12 volts or more. And then you will see the light bulb coming on and going off. Now if you put a resistor, the time it takes for it to go down to 0 intensity will be more. Alright, so understand the charge. I think I gave an example, right? Did I give an example here? Of the flow rate is highest in the beginning and all that? What example was that?
You did the light ticket booth.
Say it again?
I think you did the light bulb before.
No, some other practical example?
The ticket booth.
No.
Huh?
The ticket booth.
Yeah, the ticket booth. At the ticket booths, there's only one booth with 100 people lined up. You're all lined up like that. and suddenly the other booth opens up and ready to take people. So there'll be mad rush in the beginning, so there'll be a high current in the beginning to fill that up. But as it starts getting filled up, the flow rate will reduce, and when they're both even 50-50, then there won't be any flow rate at all. Okay? Of course, in that example, things can fail, because if one guy who's working behind the counter is more efficient, then it will establish more potential difference in between, right? So the number will actually drop faster here, and so what will happen is, like, you'll say, oh, that seems to be smaller. So you run in there. Just like traffic on the roads, you're driving and suddenly you see, oh, why is this being held up? This looks clear, so let me go that way. Let me go this way. Yeah. Now, when you connect the power supply like that, this is going to get charged to V volts. Now my question is this: what is the work done by the power supply? What is the work done by the power supply? How much work did the power supply do in order to push Q coulombs out? How much work did it do? How much? I'm talking about the power supply, this one. The power supply, how much work did it do? I mean, you're done moving charges, right? Yeah, give it another shot. What is the work done by the battery, by the power supply? What did the power supply do? It transferred Q coulombs in order to push it there across a potential difference of V volts.
QV.
QV. You've done this earlier. Flip back some of the pages and you'll see a place where it says potential difference V is the difference, what is the definition of potential difference between 2 points? Potential difference between 2 points is 1 volt when 1 coulomb is taken across and you do 1 joule. Therefore, if you take Q coulombs across a potential difference of V volts, how much work do you do? QV. Do you find it? And so when charges are being transferred from here to here, this V is not going to change. It's a power supply. The V is fixed. Whereas here the V is not fixed. What was the initial potential difference here? Zero. And then it builds up. Whereas this one is not going from 0. It stays fixed potential difference and you're transferring Q coulombs. So the answer is QV. That is the work done by the power supply. Now, what is the work done, energy stored in capacitor? What is the energy stored in the capacitor? That you can say. What is it? What is the energy stored in the capacitor? Yeah.
Like Q squared over 2C.
Which is same as what in terms of these. Half that's interesting because the battery did QV amount of work, but how much got pushed into this is only half QV. So the battery did 100 joules of work, capacitor only got 50 joules of work. What happened to the rest? Where's the other half QV gone? What happened to the others? Account for that. Where is it gone? Anyone? Yeah, Nick?
Is it heat
Heat where?
from the wires?
On the wires. Perfect. Because during the charging process, there is a current flowing through the wires. And that current is causing heating effect here. I square R, if you remember those things. Right? I square R is the power dissipated. And if it takes some time t, then I square r t is the total amount of energy involved. And so that half QB is always lost in the wires. Now what if you put a resistor here? If you put a resistor here, the current itself is going to be lower to start with, but it is prolonged for a longer time. So when the I is lowered, I square R T, T is increased, but it will always end up having the same. Yeah.
Why exactly do the wires heat? Is it because we're moving electrons?
Yeah, because as electrons go through the wires, the electrons will bump into stationary atoms, and they'll surrender their kinetic energy, and the stationary atoms will start vibrating, causing the heat. So any wire, if any current is flowing through a wire, the wire will heat up. Now, how much heat is going to be produced depends on I square R, which always depends on this, the resistance. If I take a thick wire, if I take very thick wires, then what will happen is the resistance becomes so small. So the heating effect won't be sensed by you. You won't even sense the heating effect. But if the wire is too thin, you touch the wires, you'll feel the wires warm. Have you seen that? Have you felt it sometimes?
Yeah.
You put an extension cord and then you connect your computer or whatever, and after some time just take the extension cord and touch it and you'll see it's pretty warm. That is heating effect of the electric current. Now try to take a thick cable, very thick cable, extension cord, you will hardly feel it getting heated up because it's all going less loss. It is less loss in the wires, and the loss depends on this. Okay, so the heating effect, that's why when you want to use an extension cord, a proper extension cord, you have to know how much current is actually going to flow. So if you are actually going to connect one extension cord and multiple things, imagine I'm connecting with one extension cord that, and that, everything together, that's going to be overloading on the extension cord. So you need to get some extension cords that are really thick wires. That's why when you go to Home Depot and say, right, I want an extension cord, the first thing they'll ask you is like, what are you going to use it for? They want to know what you're going to use it for. And if you say, well, I've got a table lamp, and then they'll show you the $2 one. That's okay. You know the $2 one or a $1 one that you get in dollar shops? That will be fine for just a little table light. And that also they'll ask, what kind of table light? Is it LED or is it incandescent? Because that also makes a difference. So LED will take hardly any current, therefore it is less. So choosing the right extension cord is very important. So if you're going to, like if you say, oh, my dryer is located here, but my wires are coming from there, so I need an extension cord. And you go to a $2 shop and get this extension cord and put it onto a dryer, your wires, extension cord will fry up. Okay, it won't even operate. The moment you turn it on, it's already heated and burned, melted. So you need really thick wires for that extension cord, especially for a dryer, because a dryer, the current is on the higher side. It's a lot of current. So continuous usage of that is actually going to be a lot of power, a lot of energy. Okay, so half of what is delivered by the battery or power supply is going straight away into heat loss, and the other one is only going into this. Now, remember I charged the capacitor with how many volts? I charged it with, no, the big one that gives 200 volts. So how much is the energy stored in the capacitor? Half CV squared. C was 2,200 microfarads times 200 volt squared. I'm using the equation half CV squared. Can you see that? Half CV squared. How many joules is this? How much is the energy stored in that capacitor when I just went and touched it once? As the capacitor gets charged fully, what is happening? How much? 44 joules. Now, 44 joule is actually stored in the capacitor, and when I released all that 44 joules instantaneously by touching it on the block, 44 joules in a short moment of time, only at some spot, is a lot of power. And that is why it actually causes the melting. So the block actually melts. Look at that. It's because of the touching. Aluminum is melting because of this. Right? So that's a lot of energy. 44 joules of energy is like gone. Okay, so energy stored in the capacitor. Now, connecting two capacitors together. So let's talk about one capacitor. Imagine this is a capacitor that is charged to a potential difference of 10 volts. It is charged to a potential difference of 10 volts, and it has a capacitance of 2000 microfarads. So the capacitance is 2000 microfarads and it is charged to 10 volts. Okay, so it's already getting charged. Now we have an uncharged capacitor here. This is an empty capacitor. There's no charges on the plates. But its capacitance is 3300 microfarads. See, capacitance has nothing to do with the charge sitting on the plates. You know that? Capacitance or capacitors are passive components. In electricity and electronics, there are some passive components and there are some active components. Passive components are components that has a value in material of what current is flowing through and all. So a resistor is a passive component. So that's a passive, this is a resistor. That's a resistor. This is kind of covered with porcelain because it can heat up really well. So on a circuit, if you find this one, this can be heating. I mean, it's not going to shock you, but this is going to burn your hands because that's supposed to withstand a lot of heat. And there are some others which don't heat up that much. So that's a passive, so resistors are passive components. And capacitors are passive components. The capacitance is already predetermined depending on the factors you know. It does not have anything to do with how many volts you're connecting to it. If you connect 2 volts to it, it will behave accordingly, charge accordingly. If you connect 10 volts accordingly, it will behave accordingly. So this is also a passive component. And the other passive component is an inductor. Inductor, like it's a coil. Coil. This is a transformer. So that is an inductor. So basically, transformer is an inductor. Okay, so that is an inductor. Wires wound around like that. So this is an inductor. It has a certain inductance and it is a passive component, not an active component. Why? Because its inductance is going to be some value. So we have resistance, capacitance, and inductance. Those are passive. Then there are some active components. I think the whole thing is this whole box is passive. Active components are like transistors. The transistor will behave according to what current is going in. So when the current goes in this direction, it will behave one way. If a current is inputted in some other direction, it may behave some other way. So the behavior is dependent on the current direction. So if it is a diode is something that allows current to flow only in one direction. A diode is something that allows current to flow only in one direction. So possibly this way. And it does not allow current to flow in this direction, like a bicycle valve. Have you seen a bicycle valve? Or a car valve? A valve. What does a valve's work?
It keeps it there.
Let something flow one way, and when something tries to come back, it blocks it. So it's basically like a flapper. When something goes this way, the flap opens. That way it closes. Right? Your dryer vent, exhaust fan vents. Air goes one way, it opens up, lets it go. Now if there is air coming from that direction, it shuts off. It doesn't bring anything in. Right? It's the same way in a bicycle. You connect your pump in, and then when you push the air from here, it sneaks in. But after it sneaks in, it can't come back. That's a valve. So diode is basically like a valve, but for electricity. So when you pass current this way, it lets go. When you pass current here, it works as if it's an infinite resistance. Same way transistors, triodes, and triacs and SCRs, and all the other, all the ICs and everything, they're all active components. They don't have anything as a characteristic just like that. So if I have them just like that, it doesn't have anything. Now, how much current is needed to make it work? There's a minimum current to make it work. Like I know this one will let current pass through, but if the voltage difference from here to here is a small voltage, it may not be enough to open the flaps. Just like the flapper. If the pressure from here is pretty less, the flapper will not open up. You need a certain pressure to kind of start, right? The same with the diodes. So it is active components and passive components. That's what it is. So in any circuit, you have active and passive components. So this is an active component. This is charged already, and this is uncharged, which means 0 volts. What will happen if you connect this from here to here? What will happen when the two capacitors join together? When the two capacitors join like this together, definitely this one contains charge. How much is the charge sitting on these plates? How much is charge sitting on the plates? You can calculate it. Let me know. Yeah, keep your calculators out and start punching buttons. We're going to do a lot of problems here. So you must be ready to do problems, plenty of them. How much is the charge sitting on these plates? And you know what formula you're going to use? Q is equal to CV. Yeah, multiply C times V. So it's going to be 20,000 microcoulombs. That's a charge. So what will happen as soon as you connect this capacitor? Do you think all this charge will run into this? No? Will it be like 10,000, 10,000? Share? No? What's going to happen? Yeah. What's going to happen is charges are going to flow here. So this voltage will drop. So will the voltage like be 5 and 5? Yeah. There will be more charge coming to the bottom capacitor. Because it's like a fat person and a thin person sitting for sharing one lunch. Okay, so how much this one's supposed to get is a lot. Okay, so whatever it is, we know that some charges are moving down here. Do we know the charge that is existing afterwards? No. Do you know this one? No. Do you know the potential? Do you know the potential difference finally on these plates? No. Or do you know the potential difference here across? No. It was 10 volts in the beginning, but now we have to find Q1, Q2, and V. We don't know any of those. So one thing is for sure correct, which is, yes, some charges are moving from here to here, but Q1 plus Q2 in the end should be because you charge this one. And by connecting it to somewhere else, charges cannot be created nor destroyed. They can just move around, but the total should stay the same, right, Matthew? Q1 plus Q2 is equal to 20,000 micro. I'm just leaving it, I don't want to put units there. So we have that. Now, if this one is going to have Q1 coulombs remaining at a new voltage V1 or V, what is the connection between this V and this capacitance and this Q1? So what is Q1 equal to? What is Q1 equal to? I'll call the C1, I'll call the C2, second capacitor. So Q1 is C1 times V. V is the unknown voltage. So the Q1 that's going to sit here is dependent on this capacitance. So capacitance times voltage. And this one is going to be C2 times V is equal to 20,000 micro. Now put the numbers. C1 is 2,000 micro, and I'm putting the V there, plus 3,300 micro, and then I put there. I'm not putting any units here. Can you see this is not a unit? This is the V as a variable. And this is 20,000 mu. Now I can knock off the mu's. And now what is left is 2,000 V plus 3,300 V, that is 5,300 V, is equal to 20,000. So what is V? Yep. 3.77 volts. What is it precisely? I'm going to use this number again. So what is it exactly? 3.77? 358, I'll call it 36. Okay? So get more precision there. So what's going to happen is charges are going to flow here until both capacitors will reach the same potential difference, and after that there's no potential difference. This reaches 3.77 volts, this also reaches 3.77 volts, and after that the potential difference is 0 between the two of them. So it stops charging. So no more flow will take place. Yep. So how much is the charge on the first one? It is C1V. Now can you find out how much charge is on the first one? C1 is what? 2,000 micro times 3.7736. How much is that answer? Leave the micro as it is. Leave them. How much?
7,547
Microcoulomb. Now you can find Q2. How much is remaining on Q2? C2B, which is 3,300 micro times 3.7736, because that also has the same potential difference, and that comes out to
12,400.
right? Approximately. Add this with this, it should be 20,000. So that shows you that charge is always conserved. So the Q1 is this and Q2 is this, and the charge together should be that. Now what is the energy stored in the capacitor initially, before I connected the second capacitor? What is the energy stored in the capacitor? Energy is equal to half QV. See, it's easy to use half QV there instead of half CV squared, because V is something that we found out, right? So easy to use because you know the Q, you know the C. So how much is that? Half 20,000 micro times 2,000 micro. Oh no, 10. How much is that? Right? That is the amount of energy in microns. So if I want to change it over, it's just 0.1. 0.1 joule. The amount of energy in that one is just 0.1 joule. So after you connect it, this one has energy E1, this one has energy E2. Let's find that out. After connections, what is E1? Half CV square, you can do that. Half 2000 micro V square, 3.7736. I'm just keeping that as it is. How much is that? Find it out. Same way, find out E2 is equal to half CV square, half 3,300 micro times 3.7736. Give me those numbers, Matthew. It's here. Push button. Calculate. Yeah. 0.0142.
Yeah.
And this one. Zero point
235.
02.
Yeah.
Add E1 and E2 together. What do you have? It is 0.0477. Oh, 3. 0.0377 joules. So you had 0.1 joules, and now you have only 0.03. All that. You know the reason where it is gone, right? Where did it go? Heat the wires. Now, this is a totally different situation where you had initially some energy and then it is taking some energy and dumping. That's why it's not like half. It's not going to be half unless it's like first time charging. Okay, when you're charging it for the first time, that's when it is. Questions here? All good? Let's go to some problems right now. I'm going to read out the problems. Now these are from the e-textbook, so you can actually like practice the e-textbook questions for better confidence in each of these things. Okay? I'm just reading some questions from here. What can you say about the electric field in a region of space that has the same potential throughout? What can you say about the electric field in a region of space that has the same potential throughout? Yeah.
The potential difference at big points in that space is 0.
So what is the field?
So 0.
What can you say about the electric field if you have different spots and all the potentials are the same? It's got the same potential. Yes. Yes.
There's no field.
There is no field. Zero field. Because for field to exist, you must have a potential difference. And if all of these points are exactly same potentials, then why should there be a field at all? Okay. the whole region is going to be an equipotential region, and therefore no field can exist there. All right. All right, an electric field of 640 volt per meter is desired between two parallel plates, 11 millimeters apart. How large a voltage should be applied? I'll read it again. Wait a minute. So you have a parallel plates. An electric field of 640 volt per meter is desired between the two parallel plates 11 millimeters apart. So 11 millimeters apart, you need an electric field of 640 volt per meter. Question is, how large a voltage should be applied? Like what's the potential difference that should be applied? How many volts? Yeah.
Was it 7.04 volts?
Yeah. That's right. Good one. 7.04 volts. If everyone's okay with that, we'll keep going. This is the time for you to keep working. Any questions here? And you know what formula we use is E is equal to V over D. So V is equal to ED. So you are given this and you are given that, but take care of the units. You can't use millimeters, you have to use meters. So change it to meters. Next question. What is the speed of an electron with a kinetic energy of 3.2 kilo electron volts? What is the speed of an electron? What's the speed of an electron that has an energy of 3.2 kilo electron volts? So the question is, what is the speed of an electron? The mass of an electron is 9.11 times 10 power minus 31 kilograms. Go ahead. Fine. Yeah.
Okay, sorry.
Half mv squared is equal to the energy 3.2 kilo electron volt. 1 electron volt is 1.6 times 10 power negative 19 coulombs. Joules. 1 electron volt is 1.6 10 power minus 19 joules. So kilo electron volts. Remember these things. 1 electron volt is the energy acquired by an electron when accelerated by 1 volt. Okay? So mass of the electron is given. You find the V square and then find V. That's all you have to do. And the answer is right, 3.35 times 10 to the power of 7 meters per second. Everyone's okay with it? Next one. All right. A 0.2 farad capacitor is desired. A 0.2 farad capacitor is desired. What area must the plates have if they are to be separated by a 2.2 millimeter gap? A 0.2 farad capacitance is required or desired. What area must the plates have if they are to be separated by 2.2 millimeters? Air gap. Go ahead. So the capacitance formula is epsilon naught A over D. Simple. And the question is, what is that? A. So all you do is just plug in. So A is equal to C D over epsilon naught. C is 0.2, not microfarads, but just farads. Times this one, 2.2 millimeters, change it to meters. Epsilon naught is 8.85 times 10 to the power of negative 12. And that should come 5 times 10 to the power of 7 meters squared. Yeah, 0.2 farads is a huge capacitance. That's why it's coming that big area. If you take the square root of this, it will tell you how many meters by how many meters. You just figure out. Take the square root of this number.
It's like 600 kilometers.
One way, 600, 600? Yeah. No, 600.
Like 7.
Meters or kilometers?
Kilometers.
600,000.
What do you get as the square root of this? Oh, okay, yeah, that's right. No, take the square root of that.
Yeah. Take the square root of 7.
No, this.
Yeah, it's 7.05106.
Isn't it like, it's like 7 kilometers.
Yeah.
You said 600 kilometers.
No, I said 7. I meant to your 6, I said 7.
Yeah, I thought you said 600 kilometers. That was like, that's too big. Yeah, it's around 6 point what? 7 point what?
7.05.
7.05 kilometers, which is very close to 4.5 miles. 4.5 miles like that and 4.5 miles like that. That area. If that's the area of this capacitor, then you can get 0.2 farads. That's why I said 0.2 is a big number. Yes.
Has there ever been a capacitor battery?
I mean, you don't have to make it spread out all the area. You can actually like stack it up or roll it up. If you roll up the same foils, you can just make it like a big barrel and you get it. They're tightly, like packed up. It'll be a big barrel and that will be a huge capacitance. It can store a lot. Next one. So is it clear? The charge on a capacitor increases by 18 microcoulombs when the voltage across it increases from 97 to 121. Again, the charge on a capacitor increases by 18 microcoulombs when the voltage across it increases from 97 to 121. So the delta Q that it is going through is 18 microcoulombs. The change in the charge. When the delta V, it was 97 and then from there it's going to 121. So this is a V before and that's a V after. So when this happened, this many microcoulombs extra came in. Right? So initially only 97 volts were applied, so it had some charge. But when 121 was applied, more charges flowed into it. So what is it? The question is asking what is the capacitance? So it's the same thing. If C is equal to Q over V, that means delta Q over delta V is also fine because it's a straight line, right? Between Q and V, it's a straight line. So Q divided by V is capacitance. or delta Q over delta V is also capacitance. Make sense? So all you have to do is 18 micro divided by the difference here, 24. So you get 7.5 times?
-7.
Yes. So
You just say 0.75.
That's what I did.
Then mine.
or just 0.75 microfarads. Next one. An electric field of 8.5 times 10 power 5 volt per meter is desired between two parallel plates. Again, an electric field of 8.5 10 power 5 volt per meter is desired. Between two parallel plates, each of area 35 centimeters square. Separated by 2.45 millimeters of air. Separated by 2.45 millimeters of air. What charge must be applied to each plate? What charge must be applied to each plate? What charge must be applied to the plate? Give some time. Ways of doing it. There are different ways of doing this one. But while I was deriving this equation, remember the steps that I took to go there? One of the steps is this: the flux is A, which is Q over epsilon naught. E is given, area is given, epsilon naught you know, Q you can find. That's it, straight away. That intermediate step gives you the answer straight away. You see it? Flux is equal to Q over epsilon naught. If you substitute stuff, now this information, is it required? Not required. This one is not required at all. So even if it was 5 centimeters, you're going to get the same answers. It's not required at all. So substitute, so what do you want? Q, so Q is equal to epsilon naught E A. So 8.85 times 10 power negative 12 times 8.5 times 10 power 5 times 35 centimeters square. What do you do with that?
Times 10 to the negative 4.
Times 10 to the power of negative 4, yeah. Because each centimeter is 10 power negative 2, so changing centimeter square to meter square, you've got to be a little careful. Some actually make this mistake. 35 centimeters square, you can think of it as 35 centimeters times 1 more centimeter. So then this will be 0.35 meters, and that will be 0.01 meters. You can see that it comes out 35 times 10 power negative 4. And if you work that, you will get that answer. Now, can we approach it in a different way? Yes, we can. I'll show you that also. What's the answer? 2 point?
63 times.
So 263. I know. All right. How can we work this out in a different way? I'll show you right now. The other way of working this out is they give you area, they give you gap. Can you find the capacitance?
Yes.
epsilon naught area over D, so we find the capacitance. 8.85 times 10 to the power of minus 12 times area 35 10 to the power of minus 4 over D, which is 2.45 times 10 to the power of negative 3. You have the capacitance. And then find the voltage. E is equal to V over D. So V will be equal to ED. And so you do that 8.5 times 10 to the power 5 times D is 2.45 times 10 to the power negative 3. Get that answer. So once we have the C and the V, Q is equal to CV. And you get that same answer. Yeah.
Tom and I used Q equals V epsilon naught area over D. That works too.
Say that once again. Oh, that's the next step.
No.
First define V.
Oh, you have to find V for that.
Yeah,
Yeah, I mean, any of those steps should work, technically, because final equation was this. So if you trace back and see any step before that, it should fit in and it should work.
We used E equals V over D.
You use this one,
Yeah, and then
use this one to find out V, and then plugged it into a stage that was earlier, right? Yeah, you can do that. But I think this will be faster, the flux thing will be faster. Next question. A homemade capacitor is assembled by placing two 9-inch pie pans. 9-inch pie pans. Okay. So, the pie pans are made of aluminum. So 9-inch pie pans, when they say 9 inches, it's the diameter. The diameter is 9 inch, okay? So again, a homemade capacitor is assembled by placing two 9-inch pie pans 5 centimeters apart. 5 centimeters apart. And connecting them to the opposite terminals of a 9-volt battery. Connecting to a 9-volt battery. Estimate the capacitance. Estimate the capacitance. Why should they use the word estimate? Any clue? Yeah.
Because they put pi pans in inches.
Doesn't matter. We are going to convert it anyway to meters. So that is not necessarily. But is there any other reason why they asked you not to calculate but estimate? Yeah.
Why? Is it because it's irrational? It's probably hard to get anything.
More than that. Yeah, I mean, like it's not absolutely flat, so it's got a raised part. So that also is a reason. Any other reason? Yeah.
Because the voltage for the place is not exactly 9.
No, they told you it's 9, so you've got to believe that. What other?
It's not, is that what Nixon?
No.
It's not irrational.
It's like
No.
the area, the overlapping area of the two.
The area of overlap should be fine if you're placing over the other. The main problem is this, the gap. It's too big, 5 centimeters is that much. So will the field be uniform everywhere? Towards the edges it will actually be non-uniform. So when the plates are pretty close, the field everywhere will be very uniform. And so we take the entire area. But now when it's bulging out like that, the area and all that will be messed up. And therefore, yes, you can use the same formula, but understand that formula will be slightly wrong because of the change of the flux is not everywhere. All right, so if you do that same formula, what do you get? And this is a 9-inch, is a diameter. Diameter is 9 inch, and you know the inch is 2.54 centimeters. So if you want to change that. So, area of a circle is pi d squared over 4. Instead of using radius, I'm just using the diameter. And then this d is the gap. Now substituting stuff, 8.85 times 10 to the power of negative 12 times pi times 9 inch converted to centimeters. What is 9 times 2.54? 22.6 times 10 to the power of negative 2 squared. That's a diameter squared. Over 4 times 5 centimeters. So if you do that, you should get the answer up here. How much?
7.27 times 10 to the
Negative 12? Possibly.
Mr. C, isn't 22.6 the diameter?
Yeah.
You would need half of it.
negative 12.
No, that I put the 4 there.
Oh, okay.
Because diameter is radius is diameter over 2. So radius squared is diameter squared over 4. You don't want to, like divide and get into fractions and all that. So what is the answer? Yes, around 7 times 10 to the power negative 12. That's what the answer is. Next question on the same. They're asking what's the charge on each plate. So you know how to find the charge, right? So you know the voltage, you know the capacitance, multiply them, you get the charge, right? The electric field halfway between the plates. The electric field halfway between the plates, right in the middle. How do you do it? The electric field halfway between the plates, in the middle. Tell me what your plan is. What formula are you going to use? Halfway between. Yes.
Isn't it KQ over R?
Now, KQ over R is mainly used for isolated point charges. Now, this is flat plates. You're going to use electric field is equal to V over D. What are you going to substitute? What are you going to put here? 9 and this one? Huh? The electric field is uniform everywhere, so it's going to be one value anywhere. Alright? It's the same value everywhere. In this corner, everywhere it's going to be E, and that is 9 volts divided by 5 centimeters converted to meter.